Greetings, everybody. Learning is a hobby here. I wanted to continue with Charles Platt's Make Electronics third edition in this video by doing experiment one and experiment two in chapter one. Um, Let me just say before I get started, I'm actually not going to do all of experiment one. In fact, I tried. I tried experiment one already, and there was a technical problem that came up, but I'll explain it again as I go through it here. So what you're going to need for experiment one, let me change my camera angle here so you can see the desk. Um, okay, so here we go. So what you need is the book. So you need the third edition of Make Electronics. You need your multimeter that, just to remind you, I'm using the kit that I got from Protect Trader. I'll have the link down below. They, again, just full disclosure, they did give me the kit for free as to promote the company, which you should check out their stuff because they are a family run company, and they have all kinds of like hobby electronic stuff there. I mentioned them in the last video, but again, I'll have all their information down in the description bar, as well as a link to my Amazon affiliate for Charles Platt's book. Okay, so you need the battery, you need the leads, you need your multimeter. Um, Before we start, let's actually go to the experiment in the book, which starts on it starts on page, what is this? Page 8. And so let me explain what happened first. Um, so in this experiment is called Taste the Power. What they ask you to do is to um, try the battery on your tongue to feel the charge from the electric the electricity from the battery, and then they tell you to dry your tongue and try it again. I actually didn't do that part because once you do that, the next thing they want you to do in the experiment is to test the resistance of your tongue by using the multimeter. Unfortunately, I ran into an issue in that part. So the multimeter here is it's a very basic multimeter. I mean, like I said, it's good for beginners, but the problem is I think maybe this one is just not sensitive enough uh to be able to what's the word, to figure out my the resist or to test the resistance of my tongue. The maximum for the ohms on here, I maybe just doesn't go high enough, because every time I tried to test the resistance of either my skin or my tongue, or I even tried with water to test the resistance of water, all I got was one on the reading of the meter, and no matter what setting I put it in, it didn't change. It always stayed at one. However, so I was worried that maybe the resistance settings on here maybe were faulty, but I tested some of I tested the leads by checking the voltage on a bunch of different batteries, and it worked. I also tried the resistance on some of the resistors that the kit came with, and all of that stuff worked perfectly fine. It was just trying to test the resistance of my skin and my tongue that just, I don't know. Maybe this meter just isn't that sensitive. So if like I said in the previous video, I'm a complete beginner. Let me know if maybe I'm just doing something wrong, or do you think maybe it is the multimeter? I really don't know. Like I said, I'm a complete beginner here, so I'm kind of at a loss for that. So that's why I said I'm only going to do part of the experiment one. And really, it's not it's not much of a part of an experiment. It's just I want to show you how to set up the multimeter. Um, because he talks about that here. So I'm going to skip all the stuff about, testing your tongue and everything. And I'll just look at some of the other important information that he gives gives you here. So let me see what. Well, oh, I should say though, don't put this stuff away because you need it for experiment 2 anyway. So here he says part of the experiment here is setting up your meter. So I guess I'll just read through what he says and then I'll show you how to do it on the multimeter that comes with the ProTech Trader kit. Okay, so it says if you have a new multimeter, does it have a battery pre-installed? This one actually does. You can see that it does by if you turn the dial, you'll see that the meter's working. So this one actually comes with a battery already installed, but be aware some multimeters don't. So if it doesn't work when you turn, right out of the box when you turn the dial, you may have to install a battery yourself. Okay, so select any function with dial and wait to see if the display shows a number. This one does. If the display window is blank, you may have to open the meter and put in a battery before you can use it. I can't tell you how to do this or what type of battery you need because the requirements of meters vary a lot. Sorry, I got a text on my phone. Just continuing here, you'll have to check the instructions that should be supplied. Meters are supplied with 2 leads, one red and one black. I'll refer to them as meter leads to distinguish them from the test leads that you'll also be using. Excuse me. Actually, the word lead can refer to almost any piece of wire connecting with a device or a component. Each meter lead has a plug on one end and a steel probe on the other, as shown in figure 117. Actually, I'll just show you the probes that come with the kit. So let me open up the bag. Right, so you actually let me put this away so I don't lose this bag for the leads. Okay, so you have a black lead and you have a red lead. Right, so this is what they're talking about. Oops. So one end of each of the leads has a plug that you can plug into that you're going to plug into the multimeter in a second, and then the other end of each of the leads has a test probe on it. All right. So let's see, where did I leave off? You insert the plugs into the meter, then touch the probes at locations where you want to know what's going on. The probes can measure electrical flow or can detect voltage. The projects in this book entail such low voltages and currents that the probes can't hurt you unless you poke yourself with their sharp ends, which do be careful because when I was testing my skin, these probes actually are pretty sharp. I don't know if you could see the ends of them here. Okay, you can buy other types of meter leads as accessories. Some are very short, and some terminate in alligator clips or little spring-loaded hooks known as mini grabbers. I like this is Charles Platt talking. I like short leads and mini grabbers myself, but meters are supplied with probes by default. Now, where should you plug the leads into your meter? This is not as simple as it sounds. So here he explains what to do. So first, I'll deal with the black lead. So let's grab the black lead. Okay. Its plug should go into the socket on your meter labeled COM, which stands for common, which is common to all of your measurements. So on this multimeter, I don't know if this will show up in the camera, but you can see the bottom plug here is labeled COM. So that's where the black lead always gets plugged into. So over here, I'm going to plug that into COM. All right. After you plug in the black lead, you'll never have to unplug it again because all measurements leave the black plug in COM. Another socket should have a letter V beside it and also a Greek symbol named omega, which looks like the sample in figure 118. It's just a capital Greek letter omega. You can see it here on the in the book. And represents electrical resistance. Okay, just so you can see on this multimeter. Hopefully I can get this to show up. That's over here. So the second plug here is where the red lead is going to get plugged into. All right, the socket may have some other symbols beside it as well, but V and omega symbol will always be there, indicating that this socket can measure electrical resistance or voltage. Plug the red lead into it. So let's do that. All right, so for my multimeter, again, I'm going to plug the red lead into that second socket. Okay. Right, so now our multimeter is set up. We just have to figure out what setting to turn the dial to. Okay, you may see a third socket labeled lowercase m, capital A, that stands for milliamps. I'll get to that later. We'll actually deal with that later on in experiment 2. Okay, you should see a fourth socket labeled 10A or 20A, meaning 10 amps or 20 amps. This too I'll deal with later. Don't use these sockets now. Okay, and then he explains a little bit about what is resistance. So let me read this out. Electrical resistance reduces the flow of electrical current. Almost every substance in the world has at least some resistance. Sorry, I'm getting messages here that's distracting me. We measure distance in miles or kilometers and temperature in Fahrenheit or Celsius degrees. We measure electrical resistance in ohms, which is an international unit named after George Ohm. And he has a little historical tidbit on George Ohm that we'll look at the end of experiment 1, who was an electrical pioneer. The Greek omega symbol that I showed in figure 118 represents ohms. For resistance above 999 ohms, the uppercase letter K is used, which stands for kiloohm, equivalent to 1,000 ohms. All the standard prefixes that you use for the metric system apply here. Okay, continuing. Just to make things absolutely clear. So sometimes, sorry, let me go back. Sometimes K has an omega symbol printed after it just to make things absolutely clear, but more often it doesn't. For example, a resistance of 1,500 ohms will usually be referred to as 1.5 K. And if you have above 999,999 ohms, uppercase letter M is used, meaning mega ohm, which is a million ohms, or 10 to the 6. In everyday speech, a mega ohm is often referred to as a meg. If someone is using a 2.2 meg resistor, its value will be 2.2 M. Right. So, and then he just says here 1 kilo ohm is equal to 1,000 ohms. 1 mega ohm is 1,000 kilo ohms, which is the same thing as a million ohms. A table showing intermediate values is in figure 121. So that's this table here. I won't bother bringing it up to the camera. If you have the book, you should take a look at it. In Europe, you may find that a resistance value has a letter R, K, or M, where you would expect a decimal point to be. This reduces the risk of errors because sometimes a point can disappear when it is badly printed. Thus, 5K6 in a European circuit diagram means 5.6 kilo ohms, and 6M8 means 6.8 mega ohms. And 3R3 means 3.3 ohms. I won't be using the European style here, but you may run into it in some circuit diagrams elsewhere. A material that has very high resistance to electricity is known as an insulator. Most but not all plastics, including the colored sheaths around wires, are insulators. A material with very low resistance is a conductor. Metals such as copper, aluminum, silver, and gold are excellent conductors. He asks here, is your tongue an insulator or a conductor? And he says, let's find out. But again, I'm going to skip the tongue assessment. He says here that, that your tongue is basically an insulator, but the more, I guess, saliva or, moisture that's on your tongue, it reduces the resistance. So in other words, it increases the electrical current that flows through your tongue, which is why when you take the battery and you touch it to your tongue, if your tongue is wet, you'll get more of a shock than if you touch it to your tongue when it's dry. At least, in theory. I didn't do the battery thing because I couldn't do the resistance thing, so there's no need to shock myself, I guess. But like I said, I think either I'm doing something wrong with the multimeter, or possibly the leads are not as sensitive as they need to be to register something on the multimeter, or maybe the multimeter itself is not as is not as accurate. I don't know. Like I said, if you know and you have an idea, let me know down in the comments because I'm kind of clueless when it comes to this stuff. So anyway, let me explain how the multimeter works at least. So if you want to test resistance, you can see here there are settings for different maximum values of the ohms that you want. So the in white here, all of these are to test. Sorry, I should be talking into the microphone here. All of these are to test um, resistance. In blue here, we have these are in the blue is volts, so that's testing voltage, and then you also have some things here labeled with a capital A, which means amps, so that measures current. But if you wanted to measure, let's say, uh, he says to measure the resistance of your tongue, you could. This is a manual multimeter. Sometimes if you get a more expensive multimeter, it'll do the ranging automatically. This one is a manual multimeter, so you have to pick the range yourself. And the way you do that is you pick the maximum value that you might expect could be possible for the thing that you're measuring. So here he says start with 200 kilo ohms for your tongue. And like I said, nothing happened when I did that. So you could try a higher maximum. The setting above that is 2,000 kilo ohms or 2 mega ohms, but even that didn't register for me. So I don't know, but that's how you do it. You pick the maximum that you would expect, and then it'll measure up to that maximum value. All right, and make sure you turn your meter off when you're not using it so you don't waste the batteries. Okay, so let's see what's left here. I guess I'll just talk about the little historical tidbit that he gives here. There's a picture here of George Ohm. I'll read the little history here. George Simon Ohm, pictured in Figure 126, was born in Bavaria in 1787 and worked in obscurity for much of his life, studying the nature of electricity using metal wire that he had to make for himself. You couldn't truck on down to Home Depot for 100 feet of doorbell wire back in the early 1800s. Despite his limited resources and inadequate mathematical abilities, Ohm was able to demonstrate in 1827 that the electrical resistance of a conductor, such as copper, varied in inverse proportion with its area of cross section, and the current flowing through it is proportional to the voltage applied to it, so long as temperatures held constant. 14 years later, the Royal Society in London finally recognized the significance of his contribution and awarded him the Copley Medal. Today, his discovery is known as Ohm's Law. When you get to experiment 4, you'll be able to discover Ohm's Law for yourself, although really you'll be rediscovering it. Okay, and then he has at the end of each experiment, he has this little section, cleanup and recycling. Here he says your battery should be almost as good as new. You can use it again. I haven't used it at all, so it's perfectly brand new. Remember to switch off your meter before putting it away. Most meters will switch themselves off after a while or will beep to remind you, but you can prolong the battery life if you switch off the meter more promptly. Okay, so that's experiment 1. Unfortunately, it was a little bit of a bust for me just because the multimeter, was giving me some issues. So we'll move on to experiment 2. And for each experiment, the book tells you, what are the things that you need. So we'll start by, see if I can get this up to the camera. All right, so I'll start by grabbing all these things from my kit. All right, so you need a 9-volt battery. This one is still wrapped in plastic, so I'll open it up now because we're actually going to use it for this experiment. Right, after this, we need a bunch of resistors, and we need actually 2 red LEDs, uh, test leads, 1 red, 1 black, 1 other color, and the multimeter. So let's start with the resistors. Okay, so you need a few different resistors. So he says uh resistor 15 ohms. We need one of those. Let me see where that is in my gigantic uh this is 15 ohms. So they give you so many resistors in the pack. I guess you use them all. I don't know, but 1.5K. I want just a 15 ohm. So these two packets are 15 ohm resistors. Right. I only need one of these though. Um, Let me just take down the packets that I need first though. So we need one of those. We need 150 ohms. See, this is 100 ohms, 10 kilo ohms. Do I not have 150? 100, 147. Yeah, it's weird. Maybe one of these. Did I misread this? 15 ohms, 15 ohms. Okay, well, we don't have a 150 ohm resistor. That's kind of strange. I don't know why they would not include that. I have a 100 ohm resistor. I have a 1.5 kilo ohm resistor. I have a 1 kilo ohm resistor. Yeah, I don't know. I guess we'll have to skip that one. Then we need a 470 ohm resistor. Okay, we have a package of that. Actually, we have two packages of that. And we need a 1.5 kilo ohm resistor. I remember seeing a package for that. We do have one of those. Here we go, 1.5 kilo ohms. Okay, and then we need two generic red LEDs. Now he doesn't say whether he just says generic LEDs. He doesn't say whether we want a 5 millimeter LED or a 3 millimeter LED. Um, I don't know. Maybe I'll pick the big ones. Just maybe it'll show up better on the camera because he doesn't really specify. So we need two of these. Okay, we need our test leads, which I already have set up. We need one other color lead. So I'll grab one of these. Maybe I'll do yellow. If I could just untangle this. Whoop. Okay, and let me actually, we only need one each of these resistors, so I will detach one from each of these bags. So these are what the resistors look like. He explains what the markings on them mean in this experiment. So I'll get to that when we get to it in the experiment. So here I'm just going to take out. Whoop, take out one of each of these. So this is the 150 ohm, which I'll leave them on the bags so I don't have to rope around for which is which. Put this on the side. All right, that's actually move this over here. All right, we need one of these 470 kilo ohm resistors. Oh, sorry, not kilo ohm. We want 470 ohms. This is 470 kilo ohms. Okay, let me just, I'm glad I caught that. 470 ohms. Let me grab one of these. All right. And again, this is what they look like. Right. You can hopefully you can see that there's like different colored bands around them. That's how you can tell which is which. Right. Let me see if I can detach one of these and put these back so I don't lose them. Right. This is 470. Now I'm looking at these 15 ohm resistors. They gave me two packages of them. I think maybe there was a mistake. Maybe there were supposed to be one package of 15 ohm resistors and one package of 150 ohm resistors, and they accidentally packaged two packages of 15 ohm resistors. That's all I can think of. I don't know, but so we'll have to skip the 150 ohm resistor because I just don't have one. Right, but we do have the 15. So grab one of these. If you're screaming that maybe the packaging is incorrect, don't worry. We're going to test the resistance, so we'll know which is which. Okay, so now I have my resistors. I have my LEDs off to the side. Okay, so let's start the experiment now. So often we need to add electrical resistance to a circuit for reasons that you'll soon see. This can be done very easily by using components known as, guess what, resistors, which have their values measured in ohms. Resistors that you acquire for the projects in this book may or may not be labeled, but that's okay. You can find out what their values are. First, I'll show you how to measure the values, and then I'll explain how to decode them. Some resistors have a number clearly stated on them in tiny print that you can read with a magnifying glass, as shown in figure 2.1 on the next page. Unfortunately, most manufacturers don't print numbers on their resistors. They use a color code. All right, so um, the parts the parts list that I provided for this experiment mentions the colors of bands printed on each resistor. You can see them in figure 2.2. The wires coming out of them are leads, even though they look unlike the leads for your meter or the test leads with alligator clips on each end. The wires coming out of your LED are leads too. Your resistors may have silver bands instead of the gold bands that I have shown, but that's okay. I'll explain the difference in a moment. First, I want you to check the values of the resistors. Make sure the red meter lead um, is still in the volts ohm socket of your meter as an experiment one. The 15 ohm resistor has a value that is much lower than that of your tongue, so you need to select a different resistance range. A value of 200 ohms is often the lowest available, so try that one. The resistor can be either way around, it makes no difference. Place it on the surface, such as wood or plastic, which doesn't conduct electricity, and hold the probes by their plastic handles. If you touch the metal ends of the probes while trying to measure the resistors, you'll also be measuring the resistance of yourself, which is not what you want. He says see figure 2.3. So let me just hold that up to the camera. So that's this one here. And you can see better on the picture here that the resistors are color coded. Okay. Press hard to make a good connection. If this seems awkward, you can try adding a couple of test leads, as in figure 2.4. Now you can do hands-free resistor testing, and the result should be very nearly the same. Write the values of your measured resistance in your notebook, remove the 15 ohm resistor, and substitute the 150 ohm resistor. After you measure that, try the 470 ohm resistor, although you'll get an overload message, or I guess that means open lead or overload. I'm not sure. OL. You'll get an OL error message until you change the resistance on your meter dial from 200 ohms to 2K. Finish by checking the 1.5K resistor. I'm betting the values which you measure will not be exactly what you expect. The values I found when I tried this were 15.1 ohms, 148 ohms, 467 ohms, and 1520 ohms. Okay. Well, let me finish reading this part and then we'll do the test here. So you have just encountered a basic truth in electronics. Measurements are never precise. Your meter isn't absolutely precise, and nor are the values of the resistors. Other factors can interfere, such as room temperature, which affects electrical resistance. There's also a tiny amount of resistance between the probes of the meter and the leads of your resistor. Your goal is to get as close as possible to accurate measurements, but total precision is impossible. That's just the way things are when you deal with electronic hardware. Okay. Let me put the book aside for a second. Okay, so let's test these with our multimeter. So we'll start with the 15 ohm and we'll go up to the 1.5 kilo ohm. All right, so this is the 15 ohm resistor, and I'll turn the setting on my multimeter as Mr. Platt suggests to 200 kilo ohms. Right, and then we apply the test leads. He says it doesn't matter which way you do it. So you just apply the test leads to both ends of or both leads rather, of the resistor. And whoops. Well, this too high, maybe. Let's try 20 kilo ohms. So here I'm getting 0.02 kilo ohms. Actually, if I go a little bit lower to a max of 200, looks like it. Yeah, looks like I'm getting 15 ohms, almost exactly. I just want to see what happens if I put it on a lower setting. Yeah, so it looks like like roughly 16 ohms. So I get 15.7. So if I round up, it's like, yeah, between 15 and 16 ohms. So like he said, not exact. So I'll put that one aside, and now we'll test the 470 ohm one, which I need a higher setting for. Here, I'll put it on 2000 ohms. The 2000? Yeah, 2000 ohms. Whoops. Okay, and touching the leads to the test probes to the leads, we get 464. So this was labeled 470. So not exact, but pretty close. 464 ohms. Okay, and then finally I have the 1.5 kilo ohms resistor. So I'm going to put that on 200 kilo ohms so that I can measure this accurately. So here I get between 1.5, 1.6. So yeah, if I put maybe up to 2000 kilo ohms, that's not as accurate. Yeah, it looks like almost spot on 1.5. I'm sure if there are more decimal places, it's not exact. But okay, so all of these resistors work out to what they should. I'm actually, you know what? I'm actually curious. I want to see if I test this other package of 15 ohm resistors. I want to make sure that these are actually 15 ohms and not 150 ohms. Why not? I have the machine out, so All right, let me test one of these. Yeah, unfortunately, there it's 15 ohms, not 150. So we definitely are missing the 150 ohm resistors. Okay, I probably could have used the 100 ohm ones. I'm sure it doesn't matter, but I want to stick. This is the second experiment that we're doing, so I want to stick close to what he has in the book. So, okay, so that's the first thing. We tested our resistors, so and they have, close to the values that they say on the packaging. And also you could read the bands, the colored bands on there, and that'll tell you what they are. Right. So going back to the book. All right, decoding a resistor. Now that you've verified your resistor values, more or less, I'll explain their coding. The system is shown in figure 2.5. Let me just show you here so you can see. Let me move the microphone a little bit. I'll explain the picture here. So if this is a resistor and it has three bands and then a space and then another band, what these tell you is first digit, second digit, and then how many zeros. And then this last digit, this last band tells you how accurate the this rating is. So it tells you like if it's I think if it's a silver band, it's up to 10% accurate, and if it's a gold band, then it's up to 5%, I believe, accuracy. And if you have four bands and then a space and then a band, then this tells you the first three digits, how many zeros, and again the gold or silver band here tells you the accuracy. So that's basically how it works, and the different colors stand for different digits. So for example, Um, so here it says black is 0. Um, it's kind of hard to see this color in this light. I think it's purple is 1, red is 2, orange is 3, yellow is 4. Oh, maybe 1 is brown. Sorry, the lighting that I have from this lighting kit is kind of making the colors look a little bit weird. 1 I think is brown. So black is 0, brown is 1, red is 2, orange is 3, yellow is 4, green is 5, blue is 6, purple is 7, gray is 8, and then white is 9. So that those represent the digits. Okay, so ignore the color of the body of the resistor. If there's a silver or gold stripe, turn the resistor so that the stripe is on the right-hand side. Silver means that the value of the resistor is accurate to within plus or minus 10%, while gold means that the value is accurate to within plus or minus 5%. These percentages are known as the tolerance of the resistor. Some resistors have a 1% tolerance, or even better, in which case they won't have. So I'm like hunched over here. Let me move this back a little bit. They won't have a silver or gold stripe, and some other color will be used. Whatever it is, you will find a gap between it and the other stripes, this gap being wider than the gaps among the other stripes. At the left end of the resistor will be 3 or 4 colored stripes. If the group consists of 3 stripes, the colors of the first 2 tell you the first 2 digits in the value of the resistor. If the group consists of 4 stripes, the colors of the first 3 tell you the first 3 digits of the value of the resistor. The last stripe in the group tells you how many zeros follow the digits in the value of the resistor. For example, look at your 1.5K resistor. Its colors are brown, green, and red, which stand for 1, 5, and 2 zeros. In other words, 1500, which is 1.5 kilo ohms. A resistor with a group of 4 colored stripes is likely to have a better tolerance than 5%. The exact tolerance is not important for the projects in this book. Okay, he has a section here that's called mysterious numbers. If you check a few resistors for or shop for them online, you'll notice that the same pair of digits keep turning up in hundreds of ohms. We often find 100, 150, 220, 330, 470, and 680 in thousands of ohms. The typical sequence is 1.0 kilo ohms, 1.5 kilo ohms, 2.2 kilo ohms, 3.3 kilo ohms, 4.7 kilo ohms, and 6.8 kilo ohms. In tens of ohms, we find 10, 15, 22, 33, 47, 68. Why is this? And then he explains it here. Long ago, manufacturing resistors accurately was a challenge, so the tolerance was 20%. In other words, the actual value could be a full 20% higher or lower than it was supposed to be. In the case of a 15 kilo ohm resistor, its actual resistance could be as low as 12K, because 15 kilo ohms minus 20% is 12 kilo ohms, or 1200 ohms, if you like. On the other hand, a 10K resistor could have a value 20% higher, like this. 10 kilo ohms plus 20% is 12 kilo ohms. So a 15K resistor and a 10K resistor might both have the same value. And there was no point in manufacturing resistors with intermediate values. Figure 2.6 illustrates this. The white numerals are the nominal values to create resistors, meaning the values that manufacturers are trying to achieve. You can see how cleverly they were chosen so that the range of possible values, 20% above and below, allowed hardly any overlap. Resistors are manufactured much more accurately today, but everyone got into the habit of using the old range of values, and these are still the ones that you are most likely to find. Bearing this in mind, I have used them throughout this book. So he gives a chart here that shows that, but I don't know if that's going to show up on the camera. I'll try, but hopefully you purchase the book yourself. Let's see, where is it? Over here. And you can read the chart yourself. So that's the chart I'm talking about. Okay, now finally we can get to creating our first circuit. Take a look at one of your red LEDs. So I have one of those here. Old-fashioned light bulbs wasted a lot of power by converting electricity into heat, but LEDs are smarter. They convert almost all their power into light, and they last almost indefinitely if you don't mistreat them. What if you do mistreat them? This may be the time to find out. Start with your 1.5 kilo ohm resistor. That's the one with brown, green, red colored bands. Grip it in a test lead connected with the negative side of your 9-volt battery. The resistor can be either way around, it doesn't care. Now use your test lead to grip your LED as in figure 2.7. I'll show you the pictures in a second. You do need to be careful to connect the LED to the right way around, as shown. When you pass electric current through an LED, its longer lead must always be more positive than its shorter lead, as if the long lead had some extra length added to it. So that's, I guess he's giving a way of remembering which side goes to the positive. Touch the loose leads of the LED and the resistor together. Your LED lights up. Amazing. You have your first circuit. So I'm going to do this for you guys, but before I actually do it in person, I want to show you how to do this first, the same experiment on one of the circuit simulators that I showed you in the previous video. So let me bring that up real quick, and then we'll do it in real life. Okay, so here's DC-AC Lab. I can go to begin simulation. Okay, and now I can pick my battery, and I want this to be a 9-volt battery like the one that we're going to use. So what I can do is go to the settings here, and I'll change this to a 9-volt battery. Okay, and I'll leave it in the orientation that I have it here. Then I need a resistor, and I need this to be 1500 1500 kilo ohms. Sorry, I wandered there for a second. Okay, so we want 1500. So this has to be 1, this has to be 5, and this has to be 10 to the second. But I do want this, I want to rotate this just so it's easy to hook everything up. Let me rotate this by 90 degrees. Okay, and then I need a red LED. Okay, here's one. I'm going to bring this on over here again, just to make things easy to hook up. And I want to rotate this one. Let's do 270. And notice, well, what I've noticed is, at least in the free version of this program, you can't change any of these values. The operating current here is 20 milliamps, so it will match up with the LEDs that we have here in real life. So here, actually, everything will be just as it is. And well, I don't want to say just as it is because it's a simulation, but all the measurements match up. Okay, let me move this over here. And I'll move this a little bit closer. Okay, and now I'm going to hook everything up. So I'm going to hook the battery up, and then I'll hook the resistor up to the LED, and what do you know? It lights up. Okay, so now we can try that in real life and see what happens. Okay, so I'll take one of the LEDs that I have here. And what else do we need? We need the 1.5 kilo ohm resistor. I need my battery. And I need, actually, I need some more of these clips, don't I? Let's see, I have one of them over here. I'll take the red one and the black one as well. Um, I forget where I read this, but I read somewhere that usually they use red for the positive lead and black for the negative one. Oh, I just dropped it. Right, and I'll take the black one also. Okay, and now I can hook everything up. So I want to hook the negative. Let's see, which is positive, which is negative. This is the negative side. So I'll use the black alligator lead, and I'll attach that to the 1.5K resistor. I can get the alligator clip to open. Okay, here we go. And then I'll take the red and plug that into the positive terminal of the battery and clip that onto the lead. Maybe I can hold this up so you can see one of the leads here is longer than the other. If hopefully that shows up. So the longer one is always the one that gets hooked up to the positive side of the battery. So I'll actually, let me widen this a little bit so things don't touch each other. All right, so this goes here. Okay, and then I'll take my other alligator clip and I'll attach one side to, or actually he says just touch the leads together. So maybe I'll do that. So here, if I touch the leads together, hopefully you guys, I don't know if you could see that, but the LED lights up. Okay, so that's the real life version of what we just did on DCAC Lab. Okay, so that's part one. Let's see what he wants us to do next. I'm going to leave this set up for a second and try not to touch those together. Okay, so going back to the book for a second. Okay. So polarity. When dealing with a power source such as a battery, remember the plus symbol always means positive, the minus symbol always means negative. The distinction between positive and negative is called polarity. When information from a manufacturer or a book tells you that a component such as an LED has polarity, make sure to connect it the right way around. If you connect positive voltage to the short lead of the LED instead of to the long lead, you're applying reverse polarity and the LED won't work. You may also shorten its life. What if you trim the leads on an LED to make it fit into a circuit that you're building? and you can't remember which lead is the long one anymore, not a problem. An LED of the type that you're using has a flat spot in its round base, making the shorter lead the more negative one. Let me see if I can see that on the one of the ones that I have here. I don't know if I could see that with my eyesight. I can't see what they're talking about. It's kind of dark in here too. The sun's gone down, so maybe I'll have to look at this in the light tomorrow morning to see if I can see what they're talking about. But it looks, I don't know, it looks the same to me. But like I said, my eyesight's not that great. So okay, he has a section here on schematics. Take a look at Figure 2.8, which is this figure here. That one. Oops, this one here. This is basically the schematic of the circuit that we just built. So, and notice the similarity with Figure 2.7. The circuit is the same, but I redrew it using symbols. This is known as a schematic. I will be using schematics throughout the book because they're easy to understand and they don't take too much space. You'll find more examples of schematic symbols when you get to experiment 6. Notice the two instances of polarity in Figure 2.8. The long line of the battery symbol indicates the positive side of the battery, and the big triangle inside the LED symbol always points from positive to negative. The small arrows are just there to remind you that this is a light emitting diode. Other types of diodes exist which don't emit light. In Europe, the symbol for the resistor is just a rectangle with its value printed in it. I'm using the zigzag American symbol here, and some people in Europe still use it too. Okay, and then the next part of the experiment is overloading an LED. So I want to show you this um, on the simulator first, but let me read through it and then we'll do it in real life. So sorry, just make some more space here. Now disconnect the 1.5 kilo ohm resistor and substitute the one rated for 150. I'm going to skip that part because I don't have a 150 ohm resistor. Brown, green, brown. What happens? The LED is much brighter. That's because there's less resistance. Moistening your tongue reduced the resistance between the probes of your meter. Or I guess I would have seen that if my meter was more sensitive, I guess. I don't know. So that when you applied the 9-volt battery, you got more of a tingle. Reducing the resistance in your circuit gives your LED more of a tingle. Do you think you can make it even brighter? Maybe you can guess what will happen, but guessing isn't good enough. Remove the 150 ohm resistor, substitute the 15 ohm resistor, but don't touch the wires together yet. Anyone who knows anything about electronics will be saying at this point, no, don't do that. But when someone tells me not to do something, I always want to see what will happen when I do it. One thing though, the wires may get a bit hot if you hold them together for long. If you want to be super cautious, use a glove. When the lead from the LED touches the lead of the 15 ohm resistor, for a short moment, the LED gets really bright, but no, that was too good to last. The LED fades away until there's just a dim glow. Some LEDs fail more dramatically than others. I'm not sure why. I'm not sure why. A couple of readers have told me that their LEDs split in half when they were overloaded. I haven't been able to make this happen myself, although I've tried. I do know that 3 millimeter LEDs self-destruct more quickly than 5 millimeter LEDs. Anyway, now you see how easy it is to destroy electronic components. Throw away the LED that you overloaded because it will never work again properly. Its life has been sacrificed in the interest of providing you with a learning experience. Fortunately, although LEDs are an amazing achievement in electronics, they don't cost much. The question is, why exactly did the LED burn out? You might guess that too much electric current flowed through it, but again, I don't like guessing. I think you need a way to measure current, and your meter will do it. First, though, I will give you a definition. Okay, so before we look at the definition and everything, let's actually perform the that part of the experiment. So, like I said, I want to do this on DCAC lab first, just to show you how that works, and then we'll actually destroy this this LED. Hopefully, it's uh, makes for good video. So let's see. Let me share my screen again. Okay, so what I'm going to do is I'm going to change the resistance here to I'm going to go right to 15 ohms, since I don't actually have a 150 ohm resistor in real life. Okay, so now this resistor is 15 ohms, and let's see what happens if we connect the circuit. Right, and you see that the LED burns out. Whoop. Okay, so I'll discard this LED, and now we can do it in real life. And I'll just bring another LED here. Turn it 270 degrees. And I'll hook it back up because maybe we will need it again. Okay, so here we go. Let's do this now, this experiment in real life. So I'm removing the 1.5K ohm, and I'm going to attach the 15 ohm resistor. Okay, and now did he say to hold the wires? I'm not sure if I should hold them. Let me see what he says. Hang on. Yeah, he says use your hands, but he says if you want to be super cautious, use the glove. I guess I'll just drop it if it gets too hot. So, okay, here we go. Oh boy, that was not that was not very exciting. It blew out like in a fraction of a second. Hopefully you guys got to see that, but it barely did anything. All right, well there goes that LED. So that one's trashed. So I'll just remove that one and we'll get rid of this one. Okay, now let's see what else he wants us to do. All right, this one is still good. So actually, I'm going to take this resistor off too, so I don't forget to change it out. Okay, so let's continue. Defining current. Electric current is the flow of electricity per second, usually measured in amperes, which are abbreviated as amps. The flow consists of electrons, each of which is a tiny particle carrying an electric charge. If your human senses were fast enough to count electrons as they zip through a wire, you can measure 1 amp as 6.25 quintillion electrons per second in American quintillions. Ha ha ha. Ampere basics. The ampere is an international unit abbreviated with the letter capital A. 1 milliamp, usually written lowercase m capital A, is 1/1000th of an ampere. A microamp, usually written as so you use the Greek letter mu as the prefix. So that stands for microamps, and is that's 1 microamp is 1/1000th of a milliamp. So and then here he just has the conversions. um, Measuring current. Every meter I have ever seen has a socket for measuring current labeled either 10A or 20A, telling you the maximum number of amps that it can deal with. You won't be measuring a high current like that right now. Your meter will also have a socket labeled in milliamps, measuring milliamps for measuring smaller currents. The maximum for this socket is usually printed beside it. Often it's 200 milliamps, but sometimes it's 400 milliamps. Look carefully at your meter and make a mental note of how many milliamps it will stand. So this meter here that I have actually will stand a maximum of 500 milliamps. I checked beforehand. The MA socket is often separate from all the others. It's not on this one. but not always. Some meters combine the measurement of volts, ohms, and milliamps all in one socket. An example is shown. So he has an example of that. This is a nice feature because you can leave the red lead plugged into the same socket almost all the time. Speaking about ones that have, all three together, and like this one does in the red, where I have the red lead plugged in. But your meter may have a separate socket for milliamps, as many do. The meters that I showed in figure 119 and 120 in the previous experiment have this arrangement. To measure current, it has to flow through your meter. This requires some caution because too much current can blow a fuse inside the meter, in which case you have to open the meter and remove the fuse, and then you must find a replacement fuse online that is exactly the right type. And while you're waiting for it to come in the mail, you can't measure current with your meter. In a cheap meter, the fuse may not be socketed, which makes it difficult to remove. And well, you get the idea, it's a hassle. So don't push too much current through your meter. If you take just a couple of simple precautions, it shouldn't happen. Personally, it's been about 5 years since I last blew a fuse in my meter. And at that time, I bought a couple spare fuses just in case I got careless again. For the circuit that you're using in this experiment, you can safely use the MA socket on any meter because I happen to know that you won't be measuring more than 25 milliamps. Turn the dial to the next highest value in the range, which is usually 200 milliamps. What if you didn't have me telling you how much current you would be measuring? You could do a calculation, which I'll explain in chapter 4, or you could start by using the socket labeled 10 amps or 20 amps and work downward. Current in the LED circuit. So here we're going to use our multimeter to test the current. I want you to rebuild your circuit with a new LED. Make sure you use the 1.5K resistor this time, not the 150 ohm resistor, and definitely not the 15 ohm resistor. You don't want to mistreat more LEDs than necessary. Insert the meter into the circuit as shown in figure 211, and make sure the red lead is in the milliamp socket, not the volts ohm socket, assuming your meter has a separate socket for milliamps. So this is the picture here. So I'm going to set up the circuit again, plugging it through my multimeter so I can measure the current. And then we'll do it a different way, I think, as well. Let me set this up first, and then I'll read the rest of what he says to do. So I'm going to take the 1.5 kilo ohm resistor here. Okay, and then I'll make my circuit again. Okay, so I need to, let's see, the negative side of the battery goes here. And then I have to use another clamp or lead. Oops, to the other side. Okay, and then I've attached that. Okay, attach that to one side of the LED. So the shorter side. Let me open these up. All right, and then I attach the red lead here to the red test probe. And let me make sure that I'm on the right setting on my, here we go, 200 milliamps. Okay, and then I can touch the, let me make sure this is in view for everyone to see. Then I can touch the, whoops. So desk is getting a little, little crowded here. So touch this together. And this is measuring, yeah, like five milliamps. So when the light goes on, you turn this so that the makes sense in the camera. So hopefully you guys can see that. It's like 5.1 milliamps. Okay, then Let me read the other side of the page here. now. Oops. 5.1 milliamps. Oh, sorry. Is 5.1 milliamps an acceptable current for the LED? Well, it seems okay. The LED doesn't burn out, but would it still be okay if you ran a 5.1 milliamps through it for a day or two? He says, I guess so. Uh, alternate Alternatively, do you think maybe you could get just a little more light out of the LED without damaging it? If you reduce the resistance a teeny bit, there's an easy way to eliminate the guesswork. You ask the manufacturer. And then he explains um, about data sheets for LEDs and for other items. He has something here on I think I'll let you guys read about the data sheets um, on your own if you have the book, and I'll just read the historical blurb here because the experiment is pretty much over. Um, yeah, let me just read this real quick. So, born in 1775 in France, André Marie Ampère, shown in figure 214, was a mathematical prodigy who became a science teacher despite being largely self-educated in his father's library. His best-known work was to derive a theory of electromagnetism in 1820, describing the way that an electric current generates a magnetic field. He used this principle to make the first reliable measurements of what came to be known as an amperage. He also built the first instrument to measure the flow of electricity, now known as a galvanometer. And since he seems to have had some spare time, he discovered the element fluorine. People weren't distracted by text messages and cat videos in those days. And then there's a little section here on direct and alternating current. Maybe I'll read that just because I think it's important. The flow of current that you get from a battery is known as direct current, or DC. You can think of it as a steady stream of electrons in one direction, like the flow of water from a faucet. The flow that you get from power outlets in your home is alternating current, abbreviated as AC. The live side of a wall outlet changes from positive to negative relative to the neutral side at a rate of 60 times each second in many foreign countries. Sorry, in many foreign countries, including Europe, 50 times per second. The word live is, I don't know why he's saying, I don't know who would say live, but he makes it, I don't know, he makes a statement about that. Anyway, AC is useful because your power utility company uses transformers to reduce the high voltage in power lines to a safe level for your home. And for reasons that I'll get into later, a transformer only works with alternating current. AC is also useful in motors and domestic appliances. The parts of a power outlet are shown in figure 215, which is in this diagram over here. Um, This style of outlet is found in North America, South America, Japan, and some other nations. European outlets look different, but the principle remains the same. If an appliance develops a fault, such as an internal loose wire, it should protect you by sinking the voltage through the ground socket. In England and some other countries, this may be called the earth socket. For most of this book, I'm not going to be dealing with AC for two reasons. Most simple electronic circuits are powered by DC, and the way that DC behaves is much easier to understand. You'll be continuing, here's the cleanup and recycling. You'll be continuing to use the same circuit in the next experiment, so there's nothing you need to put away, and the battery should still be good. All right. Well, I guess that's experiment one and experiment two. The next video will do experiment three and experiment four, I guess, depending on how long they are. So let me turn off my multimeter and I'll detach the battery so it doesn't drain the energy. And I guess I can leave this circuit connected this way. When we get to experiment three, we could still use the circuit. Okay, so let me say goodbye to you guys. I'll switch the camera angle here. All right, again, let me know what you guys think about this new sequence of videos. Did you like this video? Do you think I should have done things a little bit differently? Also, let me know about my new equipment, what you think about the audio and the video quality and everything. So yeah, and anything else you want to say down below, feel free. Like I said, I know nothing about, electronics. So if you know more about it than I do, then feel free to comment down below, because I'm here to learn. So I'll see you guys in the next video, and hopefully you decided to pick up a copy of the book and the kit that we're using from Protect Trader. I'll leave the links down below in the comment section. Sorry, in the description bar, if you want to pick any of those things up from Amazon or whatever. And I'll see you guys in the next video.